All right, so let's talk about sections 2, 3, and 2, 4. Lots of terminology to learn here, but once you start getting the terminology down, these two sections aren't that bad at all. So the first thing we're going to talk about is in behavior. And you should have already read the definition of in behavior in the notes. But I'm going to do these top two examples and write the in behavior statements, but the left hand and the right hand statements. So in this first graph, we look again only at what the arrows are doing. Now, this arrow is pointing both downward and leftward, which means as we keep going, the graph is going to keep doing that. So as x approaches negative infinity, that means it's going left. Y approaches negative infinity, that means it's going down. So that would be the left hand in behavior statement. The right hand one would be the one that corresponds to this arrow, and it's pointing down and to the right. So that would be as x goes to infinity, that's pointing it to the right. Y goes to negative infinity, that's pointing it down. Now, these two statements here, as x goes to negative infinity and as x goes to infinity, will always be part of your in behavior statements. It's these things that'll change depending on the graph. So if I look at the second one, example B, I look to the left arrow and see as x goes to negative infinity, because it's going to the left, y is going to infinity because it's rising. Now, if you think it's going to looks like it's leveling off or something like that, it won't actually level off unless we draw something special on the graph that we'll talk about later. But if it looks like it's rising, it's rising. Now, for the right-handed behavior, as x goes to infinity, that's always part of the right-handed behavior statement, it's pointing downward, so y would go to negative infinity. So I'll let you do 2a and 2b on your own time, and we'll compare answers when we get in class next time. Now, let's talk about extrema. Extrema can be relative or absolute, and if you read the definition, relative maxima are points that are higher than points in their neighborhood, so like here and here. Relative minima are points that are lower than things in their neighborhood. And then absolute are the highest points and lowest points on the graph. And I mentioned in the notes that you don't always have to have an absolute max or absolute min. If I had given you a graph that had arrows pointing downward, that would mean that the graph would have gone on forever downward, and there would be no absolute minimum because there's no lowest point on the graph. Now, positivity and negativity. A function is positive when it's above the x-axis and negative when it's below. So you can see here, the green areas are above, the blue areas are below, and if it's on 0, we would say the function is 0 at that point. Now, a function is increasing when it rises from left to right, decreasing when it falls from left to right, and constant if it's neither rising nor falling. So in this graph, if I were going through and marking the places where it's decreasing, it would be decreasing right down through here. Let me get a good decreasing here. It would be decreasing here. It would be decreasing here. So those would be the intervals of decrease. The intervals of increase, change colors here, make it green, would be here, here, and here. Those would be the intervals of increase. And then the constant intervals would be where the function is not changing that y value at all. So that would be right here. So decreasing means falling from left to right, increasing means rising from left to right, constant means staying the same. Now, concavity has to do with which way the curvature is actually going. Now, if concave down is like a frown, so if you drew it like this, that's concave down. Concave up is like a smile, looks like that. So if you look at this graph, concave up would be right here. And then somewhere in here, it's sometimes hard to tell where exactly it happens, it changes, where now it's opening downward. And concavity can sometimes be a little bit tough to see. So in those cases, you have to be just, willing to not be exact, but be in the neighborhood where it changes. Like I think it changes right around 3, but you could argue maybe it changed at 2.4 or 3.4, just depending upon your eyes. Now, all these linear pieces have no curvature. So it doesn't open up or down. So we would say there's no concavity there. Now, if we take this graph and we put all those concepts together, this is sort of how we describe graphs in mathematical language. And I'm going to add one more thing to this list. I also want to name the domain and range. Now, starting with x-intercepts. Now, there are 3 x-intercepts here, here, and here. And one of them is clearly -3. But the others you might have to estimate a little bit. It looks like about -1.43-ish and positive 1.3-ish. If it doesn't cross at an exact point, just do the best you can. So there's the x-intercepts. The y-intercept, pretty clearly -2. The relative and absolute extrema. We've got a relative max here and here. We've got relative mins here and here. And we've got absolute extrema here and here. So what I would write is I have relative mins at 0, -2, and at 7, 1. Relative maxes at -2, 2, and 5, 3. And my absolute max and min are the highest and lowest y values on the graph. So the absolute max is 5, because that's the highest y value you see on the graph. The absolute min is -6. So when we think about relative extrema, we want to name those as points because it gives their location. But when we think about absolute extrema, we want to give the y value. That says points. I promise it does. Now, intervals of positivity and negativity. The graph is positive here to here and here onward because it's above the x-axis, right? Now, when I go to write positivity and negativity, I could write 2 inequalities that indicate where those things are happening. So it's positive when x is between -3 and about -1.3, and from 1.3 up to 9. Now, this is called inequality notation. There is another way of writing this that I'd also like you to be comfortable with called interval notation. And the interval notation basically is like the inequality notation, but it looks a little bit different. You write x belongs to, that's what that symbol means, and then you write the lowest number in the interval, comma, the highest number in the interval. And if you're not including those numbers, which you aren't here because they're 0, not positive, you put parentheses. Then if you have another interval you want to do, like I do here, you put a union symbol, and then list that interval out as well. So if I were writing where it's negative, so that's interval notation, this is inequality notation. So if I wanted to write where it's negative, I'm just going to write it in interval notation this time. It's negative when x is between -6 and -3, and we don't include it, and from -1.3 to 1.3. All right, So that's intervals of positivity and negativity. Now, increase and decrease. Let's clean this up for a second. Well, let me erase. Okay, I guess I won't do that. So increase and decrease. It's increasing here and here and here and here. So when I write the intervals of increase, that would go from -6 to -2, and then from 0 to 2, and then from 4 to 5, and finally from 7 to 9. And it would be decreasing wherever it's falling from left to right. So it would be decreasing here and decreasing here. So the decrease would go between -3, oops, sorry, that's wrong, -2 and 0. And it also decreases from 5 to 7. And then it's constant where it's neither rising nor falling. So in this little stretch right here, constant from 2 to 4. Now, intervals of concavity. So there's no concavity in any of the linear stuff. So no concavity when x goes between -6 and -2, 2 and 4, and that's it, because those are the linear pieces. It's concave up where you look at this space right through here. It's clearly opening upward like a smile. So it goes from -2 to +2. And over here, where it's a little more subtle, to see where it stops, I'd estimate that happens probably around 6 and keeps going until you hit 9. And so it's concave down in this little area right here, which goes from 4 to, again, we estimated around 6. Now, when you're writing interval notation, one last note, it's really important to include this little x is an element thing in the front, because if you don't and you just look at this, it's going to look like a point, and it's not a point, it's an interval. All right, so we'll talk some more about this in class, and you'll get a chance to practice it out. And oops, I forgot to mention the domain and range, even after I added the question, didn't I? So domain and range, that thing where I was running a vertical line over the graph, this graph actually has points on the ends, no arrows, so it does have a domain and range that stop. And the domain of this graph, if you see it, goes from -6 to +9. Now, when I write this, because I'm including those points at the end, they actually are in the graph. If I wrote this as an inequality, it would have been -6 is less than or equal to x is less than or equal to 9. Notice when I wrote these down here, they didn't have the equal to on them. Whenever you're including endpoints in interval notation, instead of using parentheses, you use square brackets. So the domain here goes from -6 to 9, and it includes both of them. And the range, if I ran a horizontal line over this thing, the first place it would hit the graph is at -6, but this time it's going to be y, right, because it's range. And it would finally hit the graph at its last spot, I think at 5. And again, there are points on those, so we will put square brackets around them. There we go. Now we'll talk more about this in class next time.